Hello guys, welcome to the video. Today we are doing applications of differential equations. So it's a pretty tricky topic, but let's get into a few different examples that we might get. First one is kinematics. Now that should be familiar to us. We know we have displacement. We can find the first derivative, that's velocity, find the second derivative, that's acceleration. So no problems there. However, what might happen if my, say for example, velocity is no longer in terms of t, but in terms of x, which is my displacement? So how might we do that? Let's have a look at an example. Okay, so here is an example where we're using kinematics with our differential equation. So we have the velocity of a particle, so that's our dx dt, and that is equal to 2x plus 1 meters per second. X is displacement, initial displacement is -2. So find the equation of displacement in exact form, find the exact displacement after 4 seconds, and find the time of when displacement is -5. Now have a look at that displacement. dx dt is 2x plus 1. So the problem that we have here is we have our velocity, but we have our velocity in terms of displacement, as opposed to previously we've had our velocity in terms of time, and then we've got no problem. All we'd have to do is just integrate that. But now we're going to need to do a little bit more work. So let's start with part A. And so dx dt is equal to 2x plus 1. Okay. Now if I find the inverse of that, then now I have dt dx. I can use this idea that I've been working on, right, which is 2x plus 1 dx. So now if I integrate both sides, integrate the left hand side in terms of t, the right hand side in terms of x, and it's in terms of x, so it should be okay. So integral of this side, integral of that side. So the integral of dt is t plus some sort of constant equals, okay, what are we going to have here? Well, this one's going to be ln 2x plus 1. But if you think about that as a chain rule, then derivative of what's in here is 2. So I also need to times by a half, and then that's c2. Now we can, we usually want to group our constants together. So, and I could multiply everything by 2. So t plus c is a half ln absolute value of 2x plus 1, and multiply everything by 2. And if I multiply, I normally just don't care about that constant too much, guys. I just let it be c until I'm trying to solve it. So 2t plus my constant is ln absolute value of 2x plus 1. Okay, at this point here we want to use our initial conditions, okay, which is when t is 0, x is -2. So c equals 2t plus c, so t is 0, so c equals ln 2 times -2 plus 1. 2 times -2 is -4, plus 1 is -3, so it's ln absolute value of -3 is 3. So that is our c value. Okay, so I've kind of run out of room a little bit here, so let's, I'll just get rid of this bit. So what have we got now? We've got 2t plus ln 3 equals ln 2x plus 1. Okay, get rid of that, get rid of this. Okay, so I could say 2t is ln absolute value of 2x plus 1 minus ln 3. So ln 2x plus 1 over 3, just using my log laws. 3 is just a constant, so we're okay there. Alright, so now I can take the exponential of both sides. So e to the 2t is 2x plus 1 over 3, absolute value. Okay, and now let's have a think about what we've got now. Our e, this is always positive, but our initial displacement was -2. So we don't want the absolute value, we want e to the 2t to be negative 2x plus 1 over 3. Okay, so it's always going to be negative. We get that from that initial displacement there. In fact, if you guys have a look, when you plot this, then you end up with one of them could possibly be like this, and one of them could possibly be like that, and this is the -2 here. So we're going down this way here when you do your direction field, and we do want to exclude this one here. Okay, have a look at that yourself. Okay, nearly finished here. So multiply both sides by -1. So 2x plus 1 over 3 is -e to the 2t times 3 minus 1 and divide by 2. So I'm just going to say x is minus 3e to the 2t minus 1 all over 2. Okay, and that is our displacement in exact form. So this is our displacement, exact displacement that we found in part A. So then for part B, find the displacement after 4 seconds, and that's easy enough. Minus 3e to the 2 times 4 is 8, minus 1 over 2. That's it. Leave it in exact form. Part C is find the time when displacement is -5. So -5 equals -3e to the 2t minus 1 over 2. We can times by 2. Add 1. Divide by -3. So e to the 2t equals 3. And then take log and divide by 2. So I'm just going to write, that's going to be ln 3 over 2. So that is approximately 0.549306. Okay, next application we have is exponential growth and decay, which again we've done before. So we know that that is the rate of changes of the quantity is proportional to the quantity itself. So we can see we've got dq dt, and it's in terms of q. And in the past we've just we've had that one model that we can assume, and we know what it is in terms of t, but we're going to go from the ground up with this one. So let's have a look at how we might do this using differential equations. An example using exponential growth and decay. So we had the population of rabbits is growing over 2 years according to the equation. We have dp dt, we have the change in population with respect to the change in time, and that is in terms of population. So we're going to use our idea, what we've learned with differential equations, to solve this one. So very similar to the kinematics example that we just did. So I can find dt dp, that'll be 1 over 0.037p. Okay, and then dt is 1 over 0.037p dp. Right, now I have dt on one side in terms of t, and I have dp on the other side with all my p's. So now I can integrate both sides. Okay, the integral of dt is t plus a constant, and the integral on the right hand side will be 1 over 0.037 ln absolute value of p plus some sort of constant. Okay, now for this one here, we know for a population question, for example, we know the population has to be positive. Yeah, so we can really just ignore the absolute value here, because we know that p's got to be greater than 0 anyway. Otherwise it wouldn't make any sense. So I could say t plus c is 1 over 0.037 ln, and it's going to write p. Okay, so I can multiply both sides by 0.037, so 0.037t e plus that constant is ln p. And I'm running out of room here, sorry guys, I'll get rid of this. Okay, now I can take e of both sides, exponential of both sides, t plus c equals p. Okay, now for the next part, this is a trick that we're going to use fairly often. So pay attention now. So I can use my index laws. If I know if I'm adding these two, that's the same as multiplying, right? So I can write this as e to the c, e to the 0.037t. Okay, so basically this bit here is some sort of constant. Now for completion of what we've done before on exponentials, we're going to call that a, because that's going to be our initial population basically, isn't it? Okay, so just using the notation that we've done before. So P is A, e to the 0.037t, and I know that when t equals 0, the population is 12,000. So 12,000 equals A times 1, so 12,000 is A. So solve it, we have finished. P is 12,000 e to the 0.037t. So once we've got our model, then the second part of this question becomes a lot easier. What is the population after 20 years? So P is 12,000 e to the 0.037 times 20, and that is 25151.22617. So approximately, should definitely round to the nearest whole number because it's a population of rabbits. And second part, at what rate is it growing after 20 years? So what is dp dt? Well, that's 0.037 times whatever the population is, which was 25151.22617. So that is, well, that's before we round it. It is 930.59536. So approximately 931, and that's our rate of change. So that is the number of rabbits per year. Don't need years. Yeah, there we go. Third application that we might have is Newton's law of cooling, something that we're familiar with in extension 1 already. And so we know that our objects lose heat according to this law, and we know that our T1 is usually our room temperature, right? It's the temperature that our object is approaching. So again, we've got dt, capital T, in terms of time, but you'll see that we have this differential equation in terms of capital T. So we are going to use our differential equations to solve this one. So let's do an example. Okay, so now we have an example using Newton's law of cooling. So an object is heated to 250 degrees and left to cool, and the temperature in the room is 23 degrees Celsius. If the temperature of the object is 200 after 5 minutes, find its temperature after 20 and show that the final temperature of the object is 23 degrees. Okay, so I know that dt, capital T, lowercase t, k, t minus t1. Alright, now T1 in this example is 23 degrees. That's our room temperature. So dt is k t minus 23. Okay, now hopefully you can kind of pick the pattern here. I want to find the inverse of these, because over here on my left I have capital T. Okay, so I want to bring my capital T over there. So this is 1 over k t minus 23, and then dt is 1 over k t minus 23 d capital T. Alright, so sure you can pick what's going to happen here. I'm going to find the integral of both sides. Now k is a constant, so that's handy. I'm going to get t plus c1 is 1 over k ln absolute t minus 23 plus c2. Okay, so far so good. I've run out of room again, so let's get rid of this. Alright, and I can group those constants together. So I'm going to have t plus our constant is 1 over k ln absolute t minus 23. Just like that, get rid of this. Okay, so it's very similar to what we did with the last one. I can multiply by k. Not going to worry about the c though, because that's just going to be a constant no matter what. Now I take the exponential both sides, and I'm going to do the same trick here, aren't I, guys? Remember, e to the power of c is going to be my a. Okay, so it's e to the k, e to the kt, it's capital T minus 23. So t is 23 plus a e to the kt. Alright, I haven't quite got my model yet, so after 5 minutes, or the initial is 250. So when lower t is 0, capital T is 250. So 250 equals 23 plus a e to the 0 is 1, so that's it. So a is 227. Alright, now I've got my model. My model will be t is 23 plus 227 e to the kt. Alrighty. That's quite a long question, isn't it? Because I still don't even know what k is. So how do I find k? Well, after 5 minutes, my capital T is 200. So 200 is 23, 227 e to the 5k. So minus 23 divided by 227, so it's 177, 227 e to the 5k. Sorry about that. Take the log and divide by 5. I thought I'm going to run out of room. So ln 177 over 227 all over 5. And that is negative 0.04976, or approximately 0.0498. Okay, so I can put that in here. That's my value of k. So negative 0.0498 T. Okay, that is my model. So find its temperature after 20 minutes. So A is T is 20. So capital T is 23, 227 e to the minus 0.0498 times 20. Don't use that rounded k value though, guys. Make sure you actually plug it in. 106.91 degrees. Okay, so approximately 107. And for part B, show that the final temperature is 23. Well, my temperature is 23 plus 227 e to the minus 0.0498 T. So as T approaches infinity, e to the minus 0.0498 T is approaching 0. So that means, therefore, T is approaching 23. So that will be your final temperature. And that is it for this example. And the last one for us here, and this is something that is new, this is called logistic equation. So our logistic equation is when we have our population and they do grow, but they have a limiting condition or a carrying capacity. Now that kind of makes sense, doesn't it? Because populations can't just grow unabated. They're going to be restricted by something like the amount of resources or the amount of land or something like that, some other resource that limits how big the population can actually grow. So our model for this one is a dp dt, and we have our constant, and you can see we have population, and n here is a limiting condition. Okay, so now we have our population, our dp dt, so rate of change of population with time, in terms of p. Okay, so of course this is going to be a differential equation. So let's have a go at an example. Okay, here is our logistic equation example, and our final example for today. Mr. Taylor sets up a farm, that's me, with 100 cattle. Differential equation of P, the population of cattle is given by, and we have our differential. First one is a show that question, and that is just going to help us for part B, really. So the right hand side is equal to 4 over 15 1 over p plus 1 over 750 minus p. Okay, so if we've got two fractions, obviously I want a common denominator if I'm adding them together. So this one will need a 750 minus p. Actually, I'll just do this. 7 over p all over, and my common denominator is this. And then it will be 750 minus p, and then plus, and then that second fraction needs a p on the top and the bottom. So 1 times p is p, so we get that. Okay, so 750 minus p plus p, the p's cancel, that's handy. So you end up with 750 times 4 is 3,000. Well, 3,000 over 15 is 200. So 200 p, 750 minus p, and if I divide top and bottom by 200, I get 1 over 0.005 p, 750 minus p, which is the left-hand side. Okay, so you'll see that what we just did in part A is going to help us for part B. So we know dp dt is 0.005 p, 750 minus p. So dt dp is 1 over that. Okay, now this one's really hard for us to integrate, but that's why we will use the result that we did in part A. So hopefully you can see that that is actually just the left-hand side, but it's not going to help. I'm going to need the right-hand side. So dt is going to be 4 over 15, 1 over p plus 1 over 750 minus p dp. Okay, then I can integrate both sides. So I end up with the integral of dt is t plus some constant, and this will be 4 over 15 ln absolute value of p. Okay, and then this one's going to be ln absolute value of 750 minus p, but that's a minus p, so that's going to be a negative, and then plus some constant. If I multiply everything by 15 over 4, so I'll get 15t over 4 plus that constant equals, now using my log laws, ln absolute value of p over 750 minus p. So now I can take the exponential of both sides. E to the 3.75t. Now remember, e to the c, we're calling that a, so I'm just going to put that there. And that's the absolute value of p over 750 minus p. And we know that my population is starting at 100, starting with a positive. That's going to be a positive, so I can get rid of the absolute value there. Okay, and this is going to be a little bit tricky, so I'm just going to get rid of this. I'm running out of room. Alright, so we have a e to the 3.75t equals p over 750 minus p. Okay, so if I multiply both sides by 750 minus p, then I get 750 times a e to the 3.75t minus p a e to the 3.75t, and that all equals p. I'm trying to make p the subject, so if I add this term to the other side, so I'll get p plus p a e to the 3.75t equals 750 a e to the 3.75t. Take out p as a common factor on the left hand side, and then divide by 1 plus a e to the 3.75t. So p 750 a e to the 3.75t over 1 plus a e to the 3.75 t. Okay, now we need to find a. It might actually be easier for us to use this to find out a. So when t equals 0, p is 100, that's my initial amount of cattle. So a equals, using this formula here, a equals 100 over 650, which is 2 and 2 over 13. Okay, and then let's use that value of a in here. Okay, we've got a in 2 spots. So get rid of that. Alright, so P is 750 times 2 over 13 e to the 3.75 t over 1 plus 2 over 13 e to the 3.75 t. Okay, now if I multiply everything by 13 and I divide all my terms by e to the 3.75 t, then I end up with 1500 over 13 e to the minus 3.75 t plus 2, which is what we required. Okay, so part C, all we are doing is substituting. So after 1 year, so t equals 1, so P is 1500 over 13 e to the minus 3.75 times 1 plus 2, and that is equal to 650.553, so 651. And when t equals 3, then P will be 1500, 13 e to the minus 3.75 times 3 plus 2, and that is 749.937, approximately 750. Okay, and part D is what is the maximum possible population for the cattle. So you can just have a look at that model. What is our limiting capacity here? And if we think about t approaching infinity, 13 e to the minus 3.75, because it's got a negative power, that's going to approach 0. So your denominator is approaching 2, so that would mean P is approaching 1500 over 2, so it is approaching 750. So this farm has the capacity to hold 750 cattle, but then the resources, that's about all that they can hold. So that is it. What is the maximum possible population? 750. Okay, pretty tricky question, that one. Have a go back over the video if you need help, and I will see you in the next video. Goodbye.